All right, in this video, we're going to look at how we can use triple integrals to compute volumes of regions in three-dimensional space. So recall our discussion from sections 14.1 and 14.2 on single and double integrals and how they related to lengths of intervals and areas of regions. Okay, so if I am just taking the integral of dx over an interval from a to b, right, we said that if we think about this as a partition of our interval first as a bunch of little differential lengths, then this integral is just going to sum those differential lengths as we go from a to b. And so that in turn will give us the total length of this interval, which is just equal to b minus a. Okay, and then going up a dimension, we looked at the double integral of dA over a region R. And there we were saying, well, this is really just looking at a partition of our region R into a bunch of differential rectangles. And dA is just the area of each one of these little differential rectangles. And our integral is summing up all those areas as we range over the region. So this integral in turn will give us the area of that region R. All right, so then by extension, just going up another dimension, if I took the triple integral of dv over a region E in three-dimensional space, now I'm looking at a bunch of little differential volumes, right, dv, of these little differential regions. And if I sum those up as we range over the region E, this triple integral then will give us the volume of the region E. Okay. So with that in mind, let's go ahead and look at how we could go about setting up in a volume integral as an iterated integral. So here I have the region E in three-dimensional space, and it's bounded by this top surface in blue, given by the equation z equals h of xy, and it's bounded below by this the bottom surface in yellow, whose equation is z equals g of xy. And this is all happening over this region D down here in the XY plane. So you can imagine just projecting all of, like, basically just squishing this down onto the XY plane, and you're going to see this region D. Okay, so if I want to compute the volume of the region E here, well, as we just said, the volume would be the triple integral over the region E of dV. And first, I'm going to go ahead and look at thinking about letting z vary. Okay, so imagine fixing a point xy in your region D, and then let z vary from bottom surface to top surface. Okay, so that's what this inequality here is indicating. All right, so for a fixed xy, we're going to let z vary from the bottom surface, which is g of xy, to the top surface, which is h of xy, and these would be the bounds for z. Okay, and now what am I going to do from there? I'm going to let x and y vary over the region D. So in other words, I'm going to compute the double integral over my region D, and I'm going to have a dA out here. Okay, so a couple comments here. This integral here, this inside integral, since I'm integrating just dz, that's just simply the difference in h and g. Or put another way, this inner integral is really just measuring the height of one of these approximating pillars. And then what's this double integral out here doing? Well, it's just going to stack all of these volumes of these approximating pillars as we range over the region D, giving us in turn the total volume. So really, this is exactly the same kind of thing we did with double integration and volumes. If you go back to a problem like finding the volume of the ice cream cone shape that we had worked through in section 14.3, okay, we were looking at computing the volume bounded between a sphere and a cone, and we were looking at top surface minus bottom surface. That's really exactly what this iterated integral right here is doing for us. Okay, But now on that note, I can take this even further, because I can now write the double integral here over the region D as an iterated integral itself. Okay, and so I've just drawn a picture here of our region D in the xy plane, and for the moment we'll just think about this as being filled out by vertical strips. It may be possible that horizontal strips are nice too, but if I'm going with vertical strips, let's say now y ranges from g of x to h of x for a fixed x. So think fix x first and let y vary between these two bounding curves. So as an iterated integral, this would say let y vary from the bottom curve g of x to the top curve h of x. And then you're going to let x vary from a to b. And the thing we're integrating is itself an integral from bottom surface capital G to top surface capital H. And then the order of integration here would be dz for the pillar height. Then we would have dy, that's going to be really the height of this vertical strip, just the difference in those two curves. And then dx, that's going to be stacking these vertical strips from A to B to fill out the region D. And it's this iterated integral that we'll go ahead and compute to find the volume of our region. And we will see this in action in the next video. All right, I'll see you there.